3, 2, 1. It's party time. All right, so we have set up the stage. Second order linear differential equations. First, you solve the associated homogeneous, then you find a particular solution, then you move on with your day. Okay. So, solving the homogeneous, second order linear differential equation, amounts to finding two linearly independent solutions, scaling them up and adding them together. Right? We call such a thing a fundamental set of solutions. As we just saw with reduction of order, if you have one solution, if you can just find one, the second one can be generated using the reduction of order technique. Okay. So that naturally leads us to the question of, all right, well, how do you even generate any solutions to begin with? Right? We've seen some canned examples, right? We've seen some pretty basic examples where it's pretty easy to guess what would work, and then from there, use reduction of order. Okay. Now, when I say we've been looking at canned examples, I really mean we've been looking at canned examples. Because the functions a2, a1, and a0 obviously will dictate what the solution is going to look like. And I've got some good news / bad news. Even the most reasonable functions out front, a2, a1, and a0, even if these are really nice, the DE can still be incredibly challenging. So for a really gentle-looking example, a2 equaling 1, a1 equaling 0, and a0 being negative x. Right? I mean, look at this. Find me the function whose second derivative is equal to x times itself. How is that difficult, right? Like, how is that an impossible problem? So, the good news is that it is not an easy problem. Or that might be bad news, right? But the good news is that makes it really interesting that something so innocuous is so challenging. Right? So in fact, this is a very special differential equation. So the solutions, as we know, there are two linearly independent functions that create the general solution here. These are known as the awary functions, and we'll get a formula for these later on in the course. And as we're going to see, there's no easy way of explaining what these things are, right? So even the most reasonable variable coefficient DEs are going to have solutions that we cannot express simply, right? They're not just going to be like cosine or log of x or even something like log of cosine, right? It turns out that some of these DEs, even ones that don't seem too crazy, have a very special type of solution. So there's a branch of math actually called special functions, which are usually devoted to functions that are solutions to certain DEs that have no simple closed form expression. And here at Iowa State, we actually have a pretty neat connection to the world of special functions. So if you go to the Wikipedia page for special functions, this is a weird thing. I've never seen this on another math subject before, where they're like, oh, here's a list of notable people from the field. So they do that for special functions. We're like, oh, here's some famous people from the world of special functions. One of them is a former Iowa State professor, James Wilson. So Professor Wilson was the director of undergraduate studies here for 14 years. He was a professor here for a very long time. So I took over the job as director of undergraduate studies from him. So while I was training to become the new director, we were meeting weekly and talking. He casually mentioned that, he's like, oh yeah, I did some work in special functions. And what he failed to mention was that he did some work with some quotes around it. By some work, I mean he has polynomials named after him. Legitimately, so, right, this is amazing what I found out. Yeah, so one of our former professors has polynomials named after him, connected to the world of special functions, the Wilson polynomials. And I was like, I didn't know, I knew Professor Wilson for many years, and then he just casually brought that up, and I looked into him like, you've had polynomials named after you, you've never told me this. Yeah. Pretty neat. So yeah, so I was saying we got a nice little connection to these sorts of things. That being said, they're not the easiest things in the world. We will attack this a little bit later on, but for now, let's make our lives a little bit easier, and we'll only consider the case where the coefficient functions a1, a2, and a0 are not varying. Right, so they are only going to be constants. So from this point forward, a2, a1, and a0 are just going to be constant functions. Okay. So that means my DEs are going to look like this. A double prime plus B y prime plus CY equals 0. Where A, B, and C are just constants. They're just numbers. Okay. Now, like I said, linear equations look a lot like polynomials, and now we're looking at something that just screams this is a polynomial in disguise. So what are we going to do? Well, let's read it again. A double prime plus by prime plus cy equals 0. I need to find a function so that when I take its derivatives, scale them up, and add them together, I get 0. So I need the function's derivatives to not look too different than the original function. Right? Because I'm going to scale and add them all up, and I need to get to 0. So the derivative of y and the second derivative of y can't deviate from y too much. Well, the derivative of e to the x is itself, so something that looks like that is probably a good guess. So, right, it seems like something that looks like e to the x, so specifically e to the mx, where m is a number, it feels like solutions should probably look like that. All right, so if we plug that in, its second derivative will be m squared e to the mx. Its first derivative will be m e to the mx. Just plug in itself to get e to the mx. I can factor out e to the mx. E to the mx is never equal to 0. So that means am squared plus bm plus c has to equal 0. So now my second order linear constant coefficient differential equation turns into a polynomial. That is not shocking that is true, but it is. So we've now turned solving a second order linear constant coefficient differential equation into solving a quadratic equation. And then that's it. Okay, so the world of linear constant coefficient second order DEs, just solve a quadratic. Oh, how hard could that be? Okay. All right, let's get let's get our feet wet. Y double prime minus 36y equals 0. Okay. So what do we know? Well, go to the auxiliary equation. Replace y with m. Replace derivatives with powers. Second derivative, second power. No derivatives, no power. Anything to the 0th power is 1. M squared minus 36 equals 0. So m is 6, or m is negative 6. So that gives me a pair of solutions, e to the 6x and e to the negative 6x, right? Right, e to the mx works if m is a root to the auxiliary equation. These are roots, so we know these are solutions. Hey, I got two solutions to a second order homogeneous differential equation. Wronskian time. Hey, Wronskian's on 0. Done. Done. I'm done. That's it. Look, I solved the differential equation, and I literally did no derivatives. I didn't do anything. I just, right, I looked at a quadratic, got its roots, looked at its Wronskian, boom, I'm done. All right, well, I did derivatives. I didn't do any integration. Maybe I should say that. Right, but, right, like, we did so much legwork, right, that when we got to this, solving it was a breeze. So, right, like, this is pretty great, right? You should be astounded by this. This is right. We did so much prep work here that this DE we dispatched of within seconds. Right, just get the roots of this quadratic. Boom. Make sure it's linear independent. We did it. That's it. We're done. That's it. So the distinct roots case here that we just saw, the quadratic, the auxiliary equation having two distinct roots. Super easy. You didn't have to do anything. And in fact, this always happens. So if you've got distinct roots to your auxiliary equation, then the general solution is just going to be scale and add those two things up. They always will be linearly independent. Right, if the roots are distinct, the Wronskian will always be non-zero. You can verify it. You're going to find that the quantity m1 minus m2 shows up, which is non-zero, so no surprise there. So for example, y double prime minus y prime equals 0, the general solution, c1 plus c2 e to the x. The auxiliary equation is m squared minus m. The roots of that are 0 and 1. We've just crushed a whole bunch of differential equations. Like really, pause for a moment and think about this. There's an entire world of second-order differential equations that we now can easily solve instantaneously with virtually no work. That is amazing. Right. This is, right. This is nuking a mosquito. This is amazing. All right. Well, right, we can shoot a bazooka at an ant all we want. Bit of an unfair fight. So let's fight something a little bit more challenging. Okay, well, all right, okay. Here we go, y double prime minus 10y prime plus 25y equals 0. Okay, okay. The auxiliary equation, m squared minus 10m plus 25 equals 0. I don't know why I said here that so again, typo. The m is not equal to 25. I even have right here m is 5, like the actual answer. Right, so m is 5. Right, you could verify that works when you plug it in. 25 plus 25 giving you 50. Negative 50 equaling 0. All right, so this auxiliary equation is a special one. It only has one root. It only has one root. Right, that factors into m minus 5 quantity squared. So we only have one solution. Okay, all right, well, we're not totally sunk, because as we learned, if you only have one solution, you can reduce the order. So applying a reduction of order, and that is not right, because I didn't include slash fraction. Oof, 2 typos on the same page. You know, my PhD has been revoked. All right. I like triple check these things, I swear. Oh no! The secret's out. I'm a hack fraud. Don't tell nobody. All right, but anyway, so you perform reduction of order, and conveniently, it just turns into x times e to the 5x. So the general solution then, c1 e to the 5x plus c2 x times e to the 5x. All right. So natural question then. All right. Well, let's say we go to the auxiliary equation, and we only have one root. We can always perform reduction of order. Was there anything special about e to the 5x? Right? Was there anything special about this case? Right? When we reduce the order, is something different going to happen? Right? We know it's going to be something times e to the 5x. Well, spoilers, nothing different happens. No matter what the root is, if you have an auxiliary equation that has exactly one root, the general solution will always be c1 e to the mx plus c2 e to the mx times x. So you just slap an x on it. And that's it. Right? So in some sense, it's actually even easier. Right? So for example, if I were to look at y double prime plus 2y prime plus y equals 0, the general solution is c1 e to the x plus c2 x times e to the x, because the root of m squared minus 2m plus 1, it's got exactly one root. M equals 1. So here we go. We've now destroyed even more differential equations. We've got now an even bigger class now of DEs that we know how to solve. And not only do we know how to solve them, they are easily solved. Right? So right, all of the legwork we've done so far have basically just ensured that in a whole world of differential equations just immediately falls to its knees. Wow, that's right. So we nuked a mosquito, we shot a bazooka at an ant, now we I don't know, did something else violent. Nuking a mosquito. Nobody actually likes mosquitoes. Everyone's fine with that. Maybe shooting a bazooka at an ant isn't fun. Shooting a bazooka at a wasp nest. Let's go with that. Wasps are terrible. Yeah. Parasitic wasps, by the way, those are the worst thing. The worst thing in existence. Anyway. Okay, so let's get a real challenge now. Okay. Let's look at y double prime plus y equals 0. Well, we know something about this. We've encountered y double prime plus y equals 0 before. Right, we know what the general solution is. We know what a fundamental set of solutions are. Cosine and sine. Ooh, wait. The method that we talked about, go to the auxiliary equation. Right, so right away, we should have been a little suspicious about this method. E to the mx. Okay. Well, here we see cosine and sine are the fundamental set of solutions for this second order linear DE. Sorry. Oh, getting a little scratchy throat right now. That auxiliary equation doesn't have any roots, so alright, well, if you don't have any roots, then we got sine and cosine, so alright, well, I guess we can't use e to the x to solve this. Or can we? Ooh. Alright, well, time to talk about my absolute favorite subject in mathematics. I cannot even begin to express my deep appreciation for the exciting world of complex numbers. All right. Not because Italian mathematicians created these things, and I am you can't see I'm wildly gesticulating with my hands. I cannot hide the fact that I am an Italian from New York, not New York City. I'm from Long Island originally, about 30 minutes away from New York City. But close enough, I guess. I don't know the accent. Everyone tells me that. It's like, oh, you don't really have the accent. I was like, I don't know. I hear it in my head. I could talk more New York for you if you'd like, but I don't know. I'll keep going. So when I was, side note, while we're here talking about accents, well, I was in Japan a couple of years ago, and we were talking about Japanese accents, because so I was in Kyoto, and one of the guys who was there was from Osaka, and I guess Osaka has like a weird accent. So my buddies who are not from Osaka were making fun of him. They were like, he sounds dumb in Japanese. And then we talked about American accents, and so I was doing my New York accent for them. Complex number, let me tell you, imaginary unit is beautiful. It's the best. All right, okay, here we go. All right. Anyway, so yeah, complex numbers. These are the coolest thing. These are just so cool. Okay, so the first thing I want to do is start a fight with everybody. I is the imaginary unit. I is not current. Do not tell me I is current. You are wrong. Do not pick a different letter. I is the imaginary unit. I squared is -1. I don't care if they told you it was current. They're wrong. I'll fight every last one of you electrical engineers. Right. And the other thing about I, do not use I to index if you're a programmer. If you're a computer engineer, you do not index with I. Index with like J or K or something. So there we go. Now comp sci get out. Okay, so I is the imaginary unit. So every complex number looks like A plus BI, where A and B are real numbers, and I is an expression with the property that squaring it gives you -1. Okay. No, so I want to stress something here. I is not equal to the square root of -1. Square root of -1 is not well defined. I get something else I'll fight you on. Square root of negative numbers, there's a way of treating them, but they're not. It's not what you want. It does not work the way you want it to. So do not think of I that way. Always think of I having the property that squaring it is -1. Okay. Okay, now that I've thoroughly angered everybody, let's keep talking about these. So every complex number, right? So it looks like A plus BI. A we call the real part of the complex number, and B we call the imaginary part. And typically we'll denote them as real part of Z and the imaginary part of Z. So that's the way we'll denote it. Don't get too sweaty about this. We're going to need to talk about imaginary part and real part. It'll just make life a little bit easier a little bit later on. So something to get used to. And something else we're going to need is the idea of a conjugate of a complex number, where if you've got A plus BI, the conjugate is A minus BI, where we take Z and put a little bar on top of it. So it turns out that this is a very important technique. Now, it's worth noting that there is a geometric representation of this. So a plus bi is a algebraic way of thinking about an ordered pair. So a plus bi, you can actually think about it as a point in the plane where the x-coordinate is a and the y-coordinate is b. So the x-axis, you can think of that as the real axis, and the y-axis, you can think of this as the imaginary axis. This is known as the argand plane, which is a way of geometrically thinking about complex numbers. It's a really neat geometry that the complex numbers do a really good job of algebraically explaining, but we don't need to get super sweaty about that stuff. But if that sounds really interesting, then you should take Math 365, Complex Variables. It's good stuff. I get to teach that class every so often, and it's a great time. All right, anyway. So what are some other things we're going to need about complex numbers? Well, it turns out that ax squared plus bx plus c equals 0, this will always have a solution. It does not matter what a, b, and c are. There were always solutions. And now the type of solutions are going to depend on what b squared minus 4ac is doing. Okay, so, right, this is called the discriminant. If the discriminant is strictly positive, you've got two distinct roots. If the discriminant is equal to 0, you have a repeated root. And if the discriminant is negative, then the roots come in a conjugate pair. So they are a complex number, plus or minus, so there's the conjugate part, where the real part is negative b over 2a, and the imaginary part is the square root of 4 minus ac minus b squared all over 2a. So it looks like the usual quadratic equation, but complex number I shows up. Okay, so great. So now we've got an answer. So any auxiliary equation that we're going to look at can actually be solved, and some of them have complex numbers. Okay, but the method that we talked about for complex numbers involved e to the mx. For solving DEs involved e to the mx. Well, now that we know the auxiliary equation might have complex numbers as its roots, that means we need to talk about a complex exponential. So the complex exponential function, exp of z, is defined as z to the n divided by n factorial, the infinite summation of that. It is a fact that this is the single most important function in mathematics. I just straight up, this, if you were to ask what's the most important function in mathematics, it's this one right here. So for any real number, exp of x is just e to the x, right? Because if you look at that, that's x to the n over n factorial. That's the Taylor series of e to the x. So we know what e to the x equals it. So since that's true for any real number, exp of z is just referred to as e to the z. I want to be really careful about that notation, right, and why I'm writing it this way. E to the x, for a real number, e to the x has a clear explanation of what it's equal to, even without a power series. E to the x, right, that is e to the power of x, right? E squared, I know what that means, it's e times itself. Square root of e, I know what that means, that is e. That is the thing that when it's multiplied by itself gives me e squared. So e to any rational number makes sense, which then means that e to any real number makes sense because every real number can be approximated with rational ones. Now for complex numbers here, right, so this is a complex exponent. That doesn't immediately make any sense, but we'll get into a little bit more of that later. Now, the last little bit we need to talk about before we jump back to the world of DEs, every property about e to the x works for e to the z. So all the things you know about e to the x, they're still true for e to the z. E to the z's got some weird stuff going on with it. We'll talk about that a little bit later. But for now, e to the x is just a special case of the complex exponential, which has all the nice properties that we normally know about e to the x. Okay. So that being said, let's revisit the second order differential equation, y double prime plus y equals 0. Cosine and sine were a fundamental set of solutions to this DE. The auxiliary equation, m squared plus 1, has a pair of conjugate roots. The real part is 0, the imaginary part is 1. So plus or minus I are solutions. That means e to the ix is a solution to this. Right, we've now defined what e to a complex number needs to be. So now, get ready, because I'm about to blow your mind. E to the ix, then, has to be a linear combination of sine and cosine, right? Cosine and sine was a fundamental set of solutions to that differential equation. So that means that e to the ix has to be a linear combo of them. Ooh. Let's get spicy. Let's plug in some numbers. If I plug in 0 into that formula, e to the 0 is still going to equal 1. Like I said, the properties of e to the z, pretty much the same ones that work for e to the x, work the same for e to the z. So here we go. 1 is equal to e to the z. Well, e to the ix we know is c1 cosine x plus c2 sine x, so plugging in x equals 0 now tells me that c1 actually has to equal 1. All right, so now I have e to the ix as cosine plus some mystery constant c2 times sine. All right. How can we figure that one out? Well, let's take the derivative of this. Okay, so like I said, e to the z behaves like e to the x. So when I take the derivative of that, the I jumps out by the chain rule. That gives me this. All right, and now, well, plug in x equals 0 again. And we'll get that C2 is I. And we have now arrived at an absolutely fundamental formula in mathematics. E to the ix coincides with cosine of x plus I sine x. So here we go. X is a real number in this case. We have now connected the exponential function to the trigonometric functions sine and cosine. Nice. And this has a name. This is known as Euler's formula. So Euler is a mathematician that you've potentially heard of. If you were to rank all of the mathematicians of all time, first place is Euler, and then there is a humongous gap, and then there's every other mathematician. And I am not joking when it comes to Euler. His influence and his accomplishments are obscene. I want to stress that his name is pronounced Euler. I know it looks like Euler, but it's Euler, hence the joke up here, right? He's German, right? We don't call him Sigmund Freud. He's Sigmund Freud. So, hence, this guy's name is Euler. That is irritating because we also have Euclid in mathematics. So there isn't an EU that we pronounce different, but that's because Euclid is Greek, so, right, we don't call him Euclid, I know, but anyway. So fun fact, Euler, so if you follow hockey, you know there's a hockey team called the Edmonton Oilers. I played intramural hockey when I was in college, and guess what dumb name we came up with for our hockey team? We were the Oilers. Herder. Yeah. It gets even worse. The soccer team that I played in grad school, I was in an intramural soccer team. We were called the Riemannian Spheres. That's even dumber. Anyway. All right, so before we go forward in using this to actually solve some DEs, there's some quick things I want to point out. E to the negative ix is the same thing as e to the I of negative x, and if we plug that into Euler's formula, that gives me cosine of minus x plus I sine of x. Well, sine and cosine, remember, are even and odd functions, respectively, so cosine of a negative is just cosine of the original. Cosine doesn't care about the minus sign. And sine is odd, which means that if you do give it a minus sign, it spits it out. So, in terms of complex numbers, the conjugate of e to the ix is e to the negative ix. That's a nice little piece of information to put in your back pocket. Every so often we're going to whip this one out, so let's have it at the ready. I'll have it in our holster. Something else that's fun to plug into Euler's formula is pi. If you pop that into Euler's formula, you get e to the I pi. That is equal to cosine of pi plus I times sine of pi. Sine of pi is 0. Cosine of pi is negative 1. And so we arrive at the most beautiful equation in mathematics. E to the I pi plus 1 equals 0. Right? And so the reason this equation usually gets referred to as the most beautiful equation in mathematics is that it cleanly and neatly illustrates multiple fundamental mathematical facts. Okay, so we have the equal sign. a key ingredient in mathematics. We have 0 and 1, absolutely fundamental numbers in mathematics. We have e, pi, and I, which all three of those are incredibly important constants in mathematics. E times I times pi, so we have multiplication, plus we have addition, e to the I pi, so we have exponentiation as well. So this formula neatly relates 5 fundamental constants using the fundamental operations of equality, addition, multiplication, exponentiation. So, and good old Euler discovered this one. So another, if I remember right, somebody else kind of knew about it, but Euler. Right, the fact we even use e is because of Euler. If you've ever wondered why we always talk about e to the x, Euler is the one who really made that number a thing. So, hence the e. And if you look a little bit more into it in mathematics, pretty much all of the notation we use is basically due to Euler. The equal sign isn't, though. Somebody else came up with that one. I forget his name. But anyway. All right. So, with all of this said, with all of this wonderful, complex equipment, we can now actually use this to solve any second-order linear differential equation whose roots are complex numbers. So, for example, the auxiliary equation for this second-order DE is m squared plus 2m plus 2. The complex roots here are -1 plus or minus I. You can verify it by using that formula I discussed earlier. Another way of doing this is completing the square. I always think that's a slick trick, but however you want to use this, you can use a quadratic equation to work it out. Now, the roots will always be a conjugate pair, so you always have a real number plus or minus a real number times I. So in this case, the real number is 1 that I'm hiding. So this tells me that I have 2 solutions to my DE, right? Now, that's great and all, but those are complex solutions. I started with real variables, I want to end with real variables, and here's where all of that little side note with Euler's formula is going to come into play and help us. So if I appeal to Euler's formula, e to the -1 plus I times x, right? Like I said, complex exponential satisfies all the things that the regular exponential does. So we can pull this apart into e to the -x times e to the ix. So distribute the I, you've got -x plus I to the x. E to a sum is still going to be e, still going to be e to a base to a sum is going to be the product of the bases to the individual pieces. That's still going to be true. E to the ix, as we noted, is cosine x plus I sine x, e to the minus x going along for the ride. And as we noted, e to the minus x is the conjugate of e to the ix, so that just turns into that. So that's kind of useful, kind of interesting. Now, what am I going to do here? Well, if you look at the two, there seems to be a way I can eliminate the I term. So if I superposition this, oh boy, came back. If we take the first one, scale it by a half, take the second one, scale it by a half, and add them together, that will get rid of the I sine terms, right? They'll cancel out, and I'll just pick up e to the -x cosine x. And likewise, if I take y1, divide by 2i, same deal here. And if you work the details out, well, you'll just get e to the -x sine of x. So it will remove the i's for us. So superposition gives me 2 solutions that, note, have no complex numbers running around. They're now real solutions. And you can check. The round scan is non-zero. A little bit of work to check this, got to do some product rules, but it will equal e to the -2x. I have 2 solutions that are linearly independent, so the general solution to this is y double prime plus 2i plus y prime plus 2i equaling 0. That's the general solution to that. C1 e to the -x cosine x plus C2 e to the -x sine x. So I used complex techniques to solve a real variable problem. That's really cool. And in fact, there are a lot of really tough real variable problems that are easily solved using complex methods. So at a little brief history, so Italians created complex numbers in the 1500s, specifically a mathematician named Cardano, Cardano and the other guy, what's his name? Oh god, I'm blanking. I'm just like, what were all the Italian names? Like Giuseppe, Ignazio, Angelo. I'm just listing off my cousin's names at this point. I'm not joking, by the way. I'm from New York, and my grandparents are first generation from Italy. So anyway, it's Cardano and the other. I can't think. Anyway, but anyway, yeah. So complex numbers first appear in the 1500s. Italians start using them to solve quadratics and cubics. René Descartes gets a whiff of this, and he mocks them. Descartes, kind of a jerk, that guy. He also thought negative numbers were a load of garbage, but so he was the one who called them imaginary numbers. That's why the name kind of stuck there. So even though they were kind of known, it really wasn't until a little bit later that they were figured out to be really useful. So even though they existed since at least the 1500s, it wasn't until Euler in the 1700s really started using them to solve problems and noted their properties. And even further still, the 1800s, when our good friend Cauchy showed up, he was the one who really showed that you can use them to solve all sorts of calculus problems. So even though they had been around for a while, it wasn't until a little later that people really realized that they were quite useful. So as we just saw here, we could use them to solve differential equations. So in fact, nothing special about the equation I just showed you. If the auxiliary equation has complex roots alpha plus I beta, and alpha minus I beta, the general solution will always be e to the alpha x cosine beta plus e to the alpha x sine beta x, where they've been scaled up by C1 and C2 and added together. So there we go, the full story here. Every second-order linear constant coefficient homogeneous differential equation is completely and utterly solved by going to the auxiliary equation and going for the roots. For the complex case, you get your alpha, you get your beta. That's it. You're done. Now, note, beta is always going to be positive, right? The plus or minus doesn't matter because cosine and sine don't care about minus signs. They will destroy them or spit them out. And we've got constant C1 and C2 here, so we don't need to worry about that. So the plus or minus is just a byproduct of the complex numbers. We don't need to get too sweaty about those. But anyway, yep, so we get roots T2 and 2 plus or minus 3i for the auxiliary equation for the second order dE. That gives me the general solution. And that's it, we're done. There we go. Every linear, constant coefficient, homogeneous second order differential equation, boom, we know how to solve it. Go to the auxiliary equation, get the roots. There are 3 possibilities, and that's it. All right. That's it. All right, so, well, now we know how to solve homogeneous equations. I guess we got to figure out how to solve the non-homogeneous ones. All right, well, that's the story for next time.